Opportunistic multi-aspect fairness through personalized re-ranking. Hello, my name is Nasim Sonboli. I'm a fifth-year PhD student at the University of Colorado Boulder. I will be the main presenter here. This paper is a result of collaboration with the following authors. Here's an overview of the topics that I will be covering in this presentation. Let's imagine a loan recommendation scenario. For example, in Kiva.org. If you're not familiar with Kiva, it is a microfinance nonprofit organization that matches lenders and borrowers all around the world. Due to various reasons, some loans on this website gather more attention than other loans. The imbalance of attention causes some loans to get funded within a few minutes to a few hours, while other loans sit on the website and start. Imbalance of attention is reinforced over time since the loans are deemed to be more important and will end up in the recommendation lists of a lot of users, which increases their exposure even more. Unfairness in exposure of loans causes an imbalance in the capital distribution between all the loans in the world. The main issue here is that the value of these items is measured based on the attention or the clicks that they gather, which is similar to what we have in e-commerce websites. But in that context, more clicks help the users figure out the quality of an item or the reliability of a seller. But in this context, these clicks measure the worth of these loans, or in other words, the fate of these loans. Popularity of a loan or the number of views a loan might receive is not a good metric to compare loans. Imagine asking yourself, which borrower deserves to be on top of the recommendation list more? Should it be the one that gets more clicks? What if these clicks are biased because lenders have different biases? So the previous methods are not applicable in this context. Due to such reasons, part of the research focus in recommendation systems have recently moved into areas with greater social impact, such as this example. Inspired by this example, we propose a re-ranker that reduces exposure unfairness or representation unfairness. There has been a phenomenal body of research, recent research on fairness and recommendation systems, which you can refer to some of them in our literature review. With few exceptions, researchers have only considered scenarios in which fairness is measured relative to a single sensitive attribute, such as race or gender. But our method improves fairness within multiple sensitive attributes simultaneously. There's usually a trade-off between fairness and accuracy. Too much sacrifice in accuracy risks the usage of the previous research. In our method, we achieve a significantly better accuracy fairness trade-off compared to the previous methods. We will also demonstrate that our approach achieves a significantly better fairness in exposure than our baselines. Fairness is a threefold notion here. Firstly, our notion of fairness is multi-sided. In other words, we try to increase fairness across multiple sensitive attributes. Secondly, by fairness, we mean provider-side fairness, which is an underappreciated problem in recommender systems. Recommender systems are multi-stakeholder settings, and fairness can be discussed for any of the stakeholders, such as users or item providers. Provider-side fairness concerns the impact of recommendation delivery on the providers of items being recommended and fair treatment of them. In our example, item providers are borrowers. Thirdly, we refer to the unrightful and unequal exposure of some groups over the others as unfairness, and we refer to it as underrepresentation. Although diversity-seeking methods might also want to increase exposure, but fairness and diversity are different goals. When we have a fairness goal, we care about the social aspects of recommendations. Increasing exposure as a fairness concern seeks to increase the prevalence of items from underrepresented providers, while diversity-based methods increase exposure regardless of this information. When diversity is invoked, it is in the service of some user-oriented goals, such as increasing user satisfaction by breaking their filter bubbles or helping a system cope with a diverse range of user intents and contexts. In this paper, our concern is more provider-centric than user-centric. Here we discuss the difference between uniform and personalized diversification in a more fine-grained manner than what is discussed in the past literature. Let me explain this idea through the figure below. As you see in the plot, the first row depicts a user profile, and based on her profile, we realize she likes different colors, but she has only preferred the scores in the past. In the second line, when we deliver recommendations while increasing the uniform diversity, we disregard this information and diversify the list based on both shapes and colors. Whereas recommending items with personalized diversification makes use of this information and only diversifies the list across colors, but keeps the shapes the same. Following the idea discussed in the previous slide, I'll walk you through a real-world example and show how we have applied this idea and what we mean by opportunistic. In this context of loan recommendations, suppose the user you prefers to lend her money to women in Kenya, first and second column in table 1, which is a user's profile, but she does not have a strong preference for a loan's economic sector shown in column 3. While the user might not respond well to loans from other countries, we can consider her open-mindedness regarding the sector feature as an opportunity to increase fairness in this area. For the sake of this example, assume loans from education and conflict zones are historically underfunded in Kenya. So these loans in these sectors are identified as protected. Now consider the recommendation results in table 2. The first two recommendations, R1 and R2, increase fairness across only the sector feature by promoting items from underfunded sectors while honoring the user's preference to lend money to Kenyan women. On the other hand, R3 might not be an effective recommendation for this user since it diversifies on the wrong dimensions, although it might still be promoting protected items. So the idea here is that basically each user presents a particular type of opportunity to increase fairness, and we try to make the most of each. Now the question is that how we should detect these opportunities. We use information entropy to measure these opportunities. The higher the entropy value is for a user on a feature, the higher her tolerance to see varied outputs within that feature. For example, the user in table 1 would have low entropy for region and gender, but higher entropy for sector. For more details on this topic, I refer you back to the paper. Now, the main two research questions here are whether users exhibit different patterns of preference across fairness dimensions, and can these patterns be exploited to improve fairness accuracy trade-off using re-ranking? We'll see. So we calculated entropy values for each dimension and realized that users indeed exhibit these different patterns of interest across different dimensions. You can see in the QA data some users have loans that vary widely across different economic centers compared to the others. We can see these differences in both the movies dataset and the QA dataset. For the sake of clarity, we only plotted 2 dimensions for each dataset. So the hypothesis here is that by learning these user-specific preferences on item features, we can improve the accuracy fairness trade-off. The most related methods to us are FAIR and PFAIR ranking algorithms. The scoring function in both methods is comparative personalization score and the personalized fairness score. The key idea is greedy augmentation of the re-ranking list, and the question is what criteria to use when scoring items for that purpose. Both FAIR and PFAIR re-rankers boost the scores of items from the protected groups when no such item has yet been added to the list. Once the group is represented, the boosting disappears, but at least it ensures minimum representation for protected groups. PFAIR adds more personalization to this process than FAIR. Using information entropy measure, which we described before, the fairness boosting term is modulated so that the users with more diverse profiles are presented with results containing more fairness, enhancing diversity. But the main issue here is that in both of these methods is that it assumes binary inclusion as a sufficient definition of fairness, and it is therefore difficult to tune it to improve the representation of protected groups in a proportional way. Due to this reason, the exposure of protected items is relatively low. We propose the opportunistic fairness-aware re-ranking OFAIR, an MMR-based method to resolve the previous issues. So in the scoring function, instead of boosting the protected items as FAIR and PFAIR were doing, we penalize the items in their features if their features are similar. And we penalize the score even more if similarity is high in the features that user is flexible to see more varied results. We implement the idea of multi-aspect fairness using a weighted cosine similarity function where we weight the items according to gamma, which is the entropy vector of users on all the feature values, and W, which is the fairness weight differentiating the protected and unprotected feature values. In a way, we boost the score of the items that are different in dimensions that users are flexible to see diversity. And by assigning high fairness weights, we boost the protected groups. To know more about the details, I'll refer you back to the paper. So as a result, OFAIR incorporates personalization at the feature level into the re-ranking process and also allows fine-grained control of the protected group promotion by using per feature weights. Here's also a diagram of our proposed algorithm. Both fairness weights and tolerance weights are calculated based on user profiles offline and will be fed to the re-ranker. The re-ranker greedily adds items to the final list as we explained. We tested our method on Kiva dataset and the movie lens dataset, which was non-negative metric factorization as the base recommender algorithm, and compared the results of OFAIR with 5 baselines. Since in OFAIR we use both fairness weights and tolerance weights, we designed our other baselines in the absence of one or the other weight factor, and we present the results in the following 2 tables. What we have here is that for every 1% accuracy loss, we show the fairness gain. In both datasets, FAIR and PFAIR both show a very low fairness result, whereas OFAIR achieves a higher exposure fairness compared to the other algorithms. Here's a better representation of accuracy fairness trade-off. Both figures show the results for just MMR-based algorithms. Algorithms are MMR, OFAIR, the 2 versions incorporating different aspects of OFAIR algorithm, tolerance-based only and fairness-based only. The figures compared ranking accuracy in terms of NDCG versus the average exposure for protected items across recommendation lists, and it shows its value at different lambdas. Lambda is a hyperparameter controlling the balance between fairness and accuracy. The general trend shows that by incorporating re-ranking, the algorithms move the fraction of protected group from 11% to 34%. In both datasets, OFAIR outperforms the other algorithms in achieving a better accuracy fairness trade-off. In the movie lens dataset, MMR with only fairness weights improves fairness more than OFAIR, but OFAIR outperforms all the previous baselines in terms of accuracy. So our opportunistic and metric-agnostic approach improves provider-side fairness in multiple sensitive attributes and does so opportunistically. And we showed that our method achieves a significantly better accuracy fairness trade-off. So here we discuss the limitations and the next steps. One limitation is that MMR-based methods try to increase diversity by eliminating redundancy, which means redundancy including the protected group. So this problem doesn't let the algorithm to guarantee proportionality and fairness, although OFAIR outperforms the previous method, it still suffers from this problem on a smaller scale. So one of the feature steps is to extend the current method and ensure proportionality and fairness. So one of the other challenges that we had in this work was a lack of data set that has user features. Due to this issue, we chose movie lens data set to show the capabilities of our method on an accessible data set. Another a potential step to take is to apply this method for other stakeholders such as consumers as well. We intend to explore further the idea of opportunity in subgroup fairness-aware recommendation, in particular when recommendations are delivered over time. Thank you so much for your attention.